Okay, so today we're going to be starting chapter 10, which is all about three-dimensional figures. So right here we have the most popular ones and the ones that we will typically be using. First is a cube. You've seen this before. It's made up of squares on all the sides, like a dice or die. A cylinder sort of looks like it has two circles on the bottom, right, and top. And it's like a can of food. Cone, upside down, it's like an ice cream cone, right? We have a pyramid, looks exactly like what you would have imagine a pyramid, 4 triangular sides and a square base, right? And last but not least, we have a sphere, which is made up of an infinite amount of circles, right? It's pretty much just a ball. All right, so let's move on. This statement says some three-dimensional solids can be formed by translating or rotating two-dimensional figures. Below we show how a sphere, a cylinder, and a cone can be formed from rotating some familiar 2D shapes. All right, let's start with this sphere. So we have a circle, right? Circle here. That's the center of the circle. And we rotate it around the center, and then we rotate a little more, and a little more, and a million times when we rotate it all the way around, we end up with a sphere. Okay? So that's one thing. Next thing we have is a cylinder, and you're probably like, what can I rotate to get this shape? Now here, imagine I have a rectangle, right? And I rotate it around 1 point. And when I spin it all the way around, I'll end up with a cylinder, right? So it's pretty much just a rectangle rotated in a circle, okay? So that's how we could get a cylinder. Now, a cone. If we did a rectangle to get the cylinder shape, how do you think we get the cone shape? We would have a right triangle, right? And we rotate that all the way around like it's spinning on an axis. We rotate it in a circle, and eventually we'll end up with the cone. All right, so any of these 3 shapes could be made by rotating. Other shapes, it's different transformations, but these 3 can all be formed by rotating two-dimensional shapes. Okay, moving on. Now we're going to talk about Euler's formula, Euler's theorem. So Euler's theorem says this: the sum of the number of polyhedron's faces and the number of its vertices is equal to its number of edges plus 2. All right, that's a lot. Let's break it down. So a polyhedron, what's a polyhedron? A polyhedron is like a polygon. Remember, a polygon is any shape made up of lines, two-dimensional. This is the same thing, except it's a three-dimensional shape now. Okay, so it's the same thing, just three-dimensional. And then it says the number of faces and vertices. So what are faces? See here what's labeled blue? That's a face. A side is a face. So like another face would be this side. And this side would be another face. And then the bottom, right, that's a face. And that's a face, right? The faces are the sides. Okay, so what are the edges? The edges are what we see here in red, I'm sorry. The edges are where the faces meet. So those are all the edges. All right, there's a lot of those. Last but not least, what are the vertices? The vertices are where the edges meet. Okay, so the vertices are all those green spots. All right, so his theorem basically is right here. The number of faces plus the number of vertices is equal to the edges plus 2. All right, so why don't we look at a couple examples of that? Okay, so this example says, what is the number of faces on a polyhedron with 12 edges and 6 vertices? So the formula is faces plus vertices equals edges plus 2. We don't know how many faces, so that's just f, plus 6 vertices equals 12 edges plus 2. Now we just solve for f, faces. So f plus 6 equals 14. Subtract 6 from both sides, and we have 8 faces. Alright, the next one says, a figure has 12 faces and 30 vertices. How many edges does it have? Okay, so 12 faces plus 30 vertices is equal to edges plus 2. 42 is equal to edges plus 2. Subtract 2 from both sides, and we have 40 edges. Okay? Alright, moving on. Cross sections. Okay, so a cross section, this says cross sections form two-dimensional figures. Often people refer to cross sections as being a slice of a solid. The result of the intersection of a plane and a solid may form more than one two-dimensional shape, depending on how the plane intersects the solid. So let's look at this circle here. When you take a slice of this circle, which is what they did right here, they took a slice, right? That's what a cross-section is. It's a slice. When they cut it, if you cut a sliver out of a ball, it would be the shape of a circle, right? So look at this question here. Can a plane slice a sphere to form a rectangle? No. There is no way you could possibly cut a sphere, one slice out of it, edge to edge fully, where you'll get a rectangle. Every time you'll get only round edges, right? You'll never get a rectangle. The edges will always be round. Okay? So the answer to that one is no. Now the next one says, a cylinder has a diameter equal to its height. Which cross-section can be formed by a plane? So right here we have a cylinder. This one says the height and the diameter are equal. Okay, so if I took a slice right down the middle, like this, I cut that out, what am I going to end up with? What's going to be left? Right, it's going to be this shape left over. And that is a square, right? And the only reason we know that this is a square is because it told us that the diameter is equal to its height. If it didn't give us that fact, we wouldn't know that it was a square. It would be a rectangle, nevertheless, but that fact tells us it's a square. All right, can I cut a circle? All right, here, let me redraw this quick. So now we have a cylinder. Can I get a circle out of it? Yeah, of course. Say I cut it sideways. Like this. This is what my cut looks like, the plane I cut across. When I cut it, the slice I end up with is going to be like this. Right? A circle. So we know we have a circle. Now, is there a way to cut it if I have a triangle? What if I go diagonally? Right? Is that going to look like a triangle? No, that's going to be a rectangle. Okay, how do I know? Right? You just have to visualize the best you can. So we know that this cannot be a triangle. Now I want to go to one of the hardest shapes. This says, what cross sections can be formed by a plane intersecting a cube? Alright, I want to pull up another video for this quick, so... Okay, so I want us to look at this video because I think it shows the cross sections of a cube really well, because the possibilities are plentiful. to say the least. All right, so look, here's one cross section. You see that moving? That's a square, right? That's one possibility. Okay, moving forward, I want you to look here. This cross section is a rectangle, right? The way they're slicing this forms different rectangles here. Another option. Okay, so what else do we have? Now look at the way they're slicing this angled. It gives us a trapezoid, right? The way they just sliced that on an angle, that gives us a trapezoid. Okay, now moving forward. Let's see what else we have. Okay, now look at this sort of sideways, slanted cut that they have. And they open it up. What's that? Cross section. Now we have a parallelogram. All right, so already now we have a square. We had a parallelogram. We had a rectangle. And we had a trapezoid. Okay, so let's see what else we have. Okay, here, now look, now they're slicing sort of on a diagonal from the quarter. They're giving us a, look at that. That one's a triangle. Now we know we have a triangle. Another option. Okay, now look, they cut it all the way to the triangle, and now they kept cutting on that angle. What is that? Now we have a hexagon. See the way they sliced that? Alright, so that adds another one to our list now. If we keep going, on a similar angle, we have a pentagon. So as you guys saw, we have lots of options and ways to cut a cube. And this is what we observed that it gave us, right? It gave us a triangle. Also an equilateral triangle. It gave us a square, a rectangle, we saw, trapezoid, parallelogram. What else do we see? We saw the pentagon. We saw a hexagon also. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 8 different cross sections just by cutting cubes in different angles and ways and planes. So it's a lot, and the visualization is hard, so just be aware, okay? Just wanted to give you guys that visualization. Okay, so moving on, we're going to be talking about isometric drawings. So this is basically just a way to take a 3D object and represent how it would look in 2 dimensions or just on paper. This grid paper you see here, this is what we call isometric graph paper, because it has 3 planes. Okay, so now I want to take a look at this structure first. The length is equal to 4, the width is equal to 2, and the height is equal to 3, right? So let's start with the width. Here we have 1 space, 2 spaces. And then again where we have the width, 2 spaces, 2 spaces, 2 spaces. Every single place that we have the width, there are 2 spaces, because that's what our width is. Okay, let's look at the height. The height is 3. 1, 2, 3. Again, 1, 2, 3. 3 spaces, 3 spaces. And then last but not least, the length is 4 spaces. We have 4 spaces here, here, here. Well, you get the idea. There. Right? And that ends up making the object look how it is. So the math is all there. We're just making the shape represented on paper. Okay? So just pay attention to the line directions. One line direction will go this way, one will be up and down, and one will be that direction, okay? Okay, let's look at this circle, this cylinder. Okay, so what do we know about this cylinder looking at the pictures? Right here, let's see, we have, this says 3. Okay, 1 space, 2 space, 3 space. So we know that the height is 3. But does that value represent the height? This value we have here. What does it represent? It represents the diameter. Okay, so the diameter is 3, which means that here we also have to have 3 across. 2, 3, 1, 2, 3. And that'll give us our circle. So we know that it should hit at the 2 mark, about halfway in each of these, and then we just connect them and draw the circle. Okay, and then here, look at where we have this 2, right here. 2 spaces is what we have as this would be the height of the cylinder, right? Now, it doesn't make sense to draw it all the way out here, because it's not actually connected to our shape. This just tells us the height of our shape where we can calculate it. Okay, and 2 from this box, 1, 2. 2 from this corner, 1, 2. So all we have to do is connect it to where we have the green, right here, and then draw that. That part will always look a little rough. Okay, you just have to get the overall idea of doing the box first by the height, width, and length, and then the rest of the shape will just sort of happen. Okay? So look at this one. This cylinder, we have 4 across here, 4 across here, and what's our, right here, 1, 2, 3. So that's 3 is the height. 1, 2, 3. 3 is the height. Okay, so we know that the height equals 3 units, and if this right here is the width is 4, the width of a cylinder, what's the width of the cylinder? It's actually the diameter. Okay, so here will be 1, 2, 3, 4, right? Because it's the diameter. So you just, again, draw your lines as you can. Start with the circle, bring it down. It just is, I'm showing you how it mathematically describes it. Okay? Okay, last but not least, let's take a look at this pyramid. Okay, so this pyramid has, let's start with the width right here. Width, 1, 2, 3. Width equals 3. Alright, now let's look at the length. 1, 2, 3, 4, 5. 5. Okay, now the height. Be careful here. The height is not this labeled in yellow. The height is where we have this perpendicular drawing, right? Because the height is from the base of the object to the top of the object in a perpendicular setting. Alright, so make sure you're using that value to find the height. So for the height, we have 1, 2, 3, 4, and then we have a half here and a half here, so the height is 5. Okay? And then we just connect the lines from each corner, right, and we end up with our pyramid. So just to, if you're looking at one of these shapes drawn in this setting, break it down